Multiplication of a vector by a scalar. We have a vector A in xy plane starting from origin point O. We can multiply this vector A by a scalar number. If k is a scalar and A is a vector, then the scalar multiple is a vector whose length is k times the length of vector A and whose direction depending upon the value k. If k is equals to 0, then after multiplication with vector A, we get 0 vector. If k is greater than 0, then after multiplication with vector A, we get k into vector A. If k is less than 0, then after multiplication with vector A, we get minus k into vector A. Let's understand it by the help of few examples. When we multiply vector A with scalar number 2, then we get 2 into vector A. The direction of vector A after multiplication with 2 remains same, but the length of vector A becomes double. When the vector is multiplied by a scalar k is equals to 2, the length of the vector increases 2 times and the direction remains the same. When we multiply vector A with scalar number minus 2, the direction of vector A reverses after becoming minus 2 into vector A, and the length of vector A increases 2 times. Here direction of vector A reverses after multiplication with negative number minus 2. So due to this negative sign, direction is reversed. Resolution of vectors. The process of splitting a vector into two or more vectors is called resolution of a vector. And the vectors obtained from this process are known as components of vector. We have vector A on Cartesian coordinate system making an angle theta with x-axis. This vector A is denoted by line OP. We can draw a perpendicular from point P on x-axis and y-axis, and it meets at point Q on x-axis and point S on y-axis. Putting arrowhead from the direction of O towards Q represents a vector AX, and putting arrowhead from the direction of O towards S gives us vector AY. Vector AX and vector AY are perpendicular to each other. That's why they are known as rectangular components of vector. So vector A is equals to sum of its components AX plus AY. Vector A is split it into its two components AX and AY. Vector AX can be written as magnitude of vector AX into unit vector along x-axis I cap. Vector AY can be written as magnitude of vector AY into unit vector along y-axis, that is j cap. According to the formula, vector is equals to magnitude of vector into unit vector. Let's say it equation number 1. Components represented in terms of vector. Considering a triangle OPQ, without considering the sides of triangle OPQ as vectors, it forms a right angle triangle OPQ. Using the trigonometric relation cos theta is equals to base upon hypotenuse. Here base is AX and hypotenuse is A. We have taken the magnitude of vectors. By rearranging, we get AX is equal to A cos theta. Let's say it equation number 2. Using the trigonometric relation, sin theta is equals to perpendicular upon hypotenuse. In triangle OPQ, hypotenuse is A and perpendicular is AY, magnitude of vector AY. After rearranging, we get AY is equals to A sin theta. Let's say it equation number 3. These equation 2 and equation 3 are showing components of vectors in terms of vectors. Its vector. Putting equation number 2 and equation number 3 in equation number 1, we get vector A is equals to ax cos theta into unit vector I cap plus ay sin theta into unit vector j cap. From triangle OPQ using Pythagoras theorem, hypotenuse square is equals to base square plus perpendicular square, taking square roots on both sides. On left hand side, square is cancelled with square root and we get hypotenuse is equals to under root base square plus perpendicular square. In triangle OPQ, hypotenuse is magnitude of vector A, base is magnitude of vector AX and perpendicular is magnitude of vector AY. Putting the values, we get magnitude of vector A is equals to square root ax square plus ay square. To determine the direction in right angle triangle OPQ, we can use the trigonometric relation tan theta is equals to perpendicular divided by base. In right angle triangle OPQ, perpendicular is magnitude of vector AY and base is magnitude of vector AX. For finding theta, we can shift tan on right hand side and we get theta is equals to tan inverse ay divided by ax. Let's say equation number C. In three-dimensional space, vector A can be written as A is equals to square root ax square plus ay square plus az square. Let's say it equation number D. Addition of vectors by rectangular components. The analytical method for addition of vectors is called addition of vectors by rectangular components. This method is more precise and accurate because it is mathematical rather than geometrical. We have vector A in Cartesian coordinate system making an angle theta A with x-axis, and we have second vector B in Cartesian coordinate system making an angle theta B with x-axis. We can add vector A and vector B by using head to tail rule to obtain resultant vector R. So tail of vector B is joined with head of vector A. Now tail of vector A is connected with head of vector B to get the resultant vector R. So the resultant vector R is mathematically R vector is equals to vector A plus vector B. Let's say it equation number 1. We can divide vector A into its components, vector components ax along x-axis and vector component ay along y-axis. We can split vector B into its two components, vector bx along x-axis and vector by along y-axis. Resultant vector r makes angle theta r with x-axis. We can divide the resultant vector r into its two components rx and ry. From the figure you can see that ax plus bx gives us rx and ay plus by gives us ry. So we can write rx is equals to ax plus bx and ry is equals to ay plus by. From figure we can write vector rx is equals to vector ax plus vector bx. According to the formula, vector is equals to magnitude of vector into unit vector. We can write vector rx as magnitude of vector rx into unit vector I cap along x-axis. We can write vector ax as magnitude of vector ax into unit vector I cap. We can write vector bx as magnitude of vector bx into unit vector I cap. So the magnitude of vector rx is equals to magnitude of ax plus bx. Let's say it equation number 2. From figure we can see that vector ry is equals to vector ay plus vector by. We can write vector ry as magnitude of vector ry into unit vector j cap along y-axis. We can write vector ay as magnitude of vector ay into unit vector j along y-axis. We can write vector by as magnitude of by vector by into unit vector j cap along y-axis. Finally, we can write magnitude of ry is equals to magnitude of vector ay plus vector by. Let's say it equation number 3. From rectangular component, we can write resultant vector r is equals to rx I cap plus ry into j cap. Let's say it equation number 4. Putting equation number 2 and equation number 3 in equation number 4, we get resultant vector r is equals to ax plus bx into I cap plus ay plus by into j cap unit vector along y-axis. By rectangular components, the magnitude of resultant vector r is equals to under root rx square plus ry square. Let's say it equation number 5. Putting values of rx and ry from equation 2 and equation 3 in equation number 5, we get magnitude of resultant vector r is equals to square root ax plus bx whole square plus ay plus by whole square. By rectangular components, the direction is theta r is equals to tan inverse ry divided by rx. Let's say it equation number 6. Putting the values of ry and rx from equation 2 and equation 3 in equation number 6, we get theta r is equals to tan inverse ay plus by divided by ax plus bx. We used head to tail rule for adding two vectors and we obtained equation A, equation B and equation number C. The same procedure can be used for any number of vectors A, B, C, D, E, F up to N to get our resultant vector R. So for more than two vectors, equation A becomes r is equals to ax plus bx plus cx plus dx and so on into I cap plus ay plus by plus cy plus so on into j cap unit vector along y-axis. Equation B can be written as magnitude of resultant vector r is equals to square root ax plus bx plus cx plus so on whole square plus ay plus by plus cy plus so on whole square. Equation C can be written as theta r is equals to tan inverse ay plus by plus cy plus so on divided by ax plus bx plus cx plus so on. Determination of angle. To find the direction theta of vector r, we use formula theta is equals to tan inverse ry divided by rx irrespective of the positive and negative signs of rx and ry. We find the direction theta of r along x-axis in counterclockwise sense and then follow the steps given here. In this figure, Rx and Ry are positive. So the angle theta R lies in first quadrant and we can determine theta R is equals to theta. So for first quadrant, theta R is equals to theta. In this figure, Rx is negative and Ry is positive. So theta R lies in second quadrant. We can determine theta r as theta r is equals to 180 degree minus theta. This angle is theta r and this angle is theta. Complete angle is 180 degree. So when we subtract 180 degree minus theta, so we get this part, this angle, that is theta r. So theta r is equals to 180 degree minus theta. In this figure, Rx and Ry both are negative, that's why theta r lies in third quadrant. We can determine angle theta r is equals to 180 degree plus theta. This angle is 180 degree and this angle is theta. So for finding theta r, we can add 180 degree plus theta to get this complete angle theta r. That's why theta r is equals to 180 degree plus theta. In this figure, Rx is positive and Ry is negative. So theta r lies in fourth quadrant. We can determine theta r is equals to 360 degree minus theta. This complete circular angle is 360 degree and this angle is theta. We can subtract 360 degree and theta to get this angle, that is theta r. Hence, theta r is equals to 360 degree minus theta. Question. Two forces. Force 1 F1 is equals to 15 Newton, making an angle theta 1 is equals to 70 degree with positive x-axis, and force F2 is equals to 25 Newton, making an angle theta 2 is equals to 220 degree with positive x-axis. Act at a point. Calculate the resultant force Fr. In this figure, we have force 1 is equals to 15 Newton, that is making angle theta 1 is equals to 70 degree along x-axis. And another vector F2 is equals to 25 Newton, making an angle theta 2 is equals to 220 degree with positive x-axis. This vector is resultant vector Fr and we have to find this resultant force. It's making an angle theta r and we have to calculate this theta r with positive x-axis. Given force F1 is equals to 15 Newton, angle theta 1 is equals to 70 degree. Force F2 is equals to 25 Newton and angle theta 2 is equals to 220 degree. We have to calculate resultant force Fr. Solution. By rectangular components, we know that resultant force Fr is equals to Frx, that is component of resultant force Fr along x-axis, plus Fry, that is component of resultant vector Fr along y-axis. Vector Frx can be written as magnitude of vector Frx into unit vector I cap along x-axis, and vector Fry can be written as magnitude of vector Fry into unit vector j cap along y-axis. We know that magnitude of vector can be written as vector Fr, that is resultant vector force, is equals to square root Frx square plus Fry square. Let's say it equation number 1. Resultant force Frx in magnitude form is equals to Frx is equals to F1x plus F2x. Let's say it equation number 2. Magnitude of resultant force Fry, component of resultant force along y-axis, is equals to F1y plus F2y. Let's say it equation number 3. We know that F1x is equals to F1 cos theta 1. Putting the values of F1 and theta 1, we get F1x is equals to 15 Newton cos 70 degree. And after solving, we get F1x is equals to 5.13 Newton Let's say it equation number 4. We know that f1y is equals to f1 sine theta 1. Putting the values of f1 and theta 1, we get f1 is equals to 15 Newton into sine 70 degree. After solving, we get f1y is equals to 14.09 Newton. Let's say it equation number 5. Similarly, for vector f2, we can write f2x is equals to f2 cos theta 2. Putting the values of f2 and theta 2, we get f2x is equals to 25 Newton into cos 220 degree. After solving, we get f2x is equals to minus 19.15 Newton. Let's say it equation number 6. f2y is equals to f2 sine theta 2. Putting the values of f2 and theta 2, we get f2y is equals to 25 Newton into sine 220 degree. After solving, we get f2y is equals to minus 16.07 Newton. Let's say it equation number 7. Putting the values of f1x and f2x from equation number 4 and equation number 6 and equation number 2, we get frx is equals to 5.13 Newton minus 19.5 Newton. After solving, we get frx, that is magnitude of resultant vector fr along x-axis, or component of vector fr along x-axis, is equals to minus 14.02 Newton. Let's say it equation number 8. Putting values of f1y and f2y from equation 5 and equation number 7 in equation number 3, we get fry is equals to 14.09 Newton minus 16.07 Newton. After solving, we get fry, component of resultant vector force fr along y-axis, is equals to minus 1.98 Newton. Let's say it equation number 9. Putting the values of frx and fry from equation number 8 and equation number 9 in equation number 1, we get fr is equals to square root into 1 minus 14.02 whole square plus minus 1.98 Newton whole square. After solving, we get fr is equals to 14.16 Newton. For the determination of angle, we write theta is equals to tan inverse of fry divided by frx. Putting the values of fry and frx, we get theta is equal to tan inverse 1.98 divided by 14.02. After solving, we get theta is equal to 7.97 degree. As we can see that frx and fry both are negative, so theta r lies in third quadrant, and it can be calculated as theta r is equals to 180 degree plus theta. Putting the value of theta 7.97 in this equation, and by adding with 180 degree, we get theta r is equals to 187.97 degree. Hence, the resultant force is Fr is equals to 14.16 Newton with direction theta r is equals to 187.97 degree.